Hello everyone, thank you for attending to this talk. My name is Juan Presenza, I'm with University of Buenos Aires, and today I'm going to present our work named Subframework-Based Rigidity Control in Multi-Robot Networks. So, it's clear that formation localization is a fundamental topic in multi-robot systems, and rigidity theory provides with necessary and sufficient conditions for localizability when only relative distance measurements are available. In this work, we present an alternative approach to the study of rigidity, which consists in expressing framework rigidity, which is a global property, in terms of a set of local subframeworks. Our main contributions are a rigidity eigenvalue upper bound, a metric and a necessary and sufficient condition for subframework-based rigidity, a scalable decentralized controller for maintaining rigidity, and a finite time messaging protocol. So, previous work regarding rigidity in multi-robot systems can be classified as continuum or combinatorial. In the first case, every agent employs the gradient of the rigidity eigenvalue and its eigenvector to guide the robot motions. Since they are global information, because they depend on the state of every robot, consensus-based estimators are developed to locally update their values. This makes the control performance dependent on the convergence property of these estimators, which vary with the network's topology and size, limiting its scalability. In the combinatorial approaches, local rules are employed to detect the robot's movements. This makes this strategy more scalable since it doesn't rely on global information. However, it's conservative in link removals, since redundant edges might not be detected locally. Also, they don't employ a rigidity metric as a control objective. Instead, rigidity is taken as a yes or no condition, so there is no optimal formation to be achieved. So, in this work, the formation is modeled as a framework, which consists of an identity graph with a set of n vertices, m edges, and the positions of every robot. The normalized rigidity matrix has a row for each edge and has the form in equation 1, which shows that it is a function of the positions. The symmetric rigidity matrix is defined as in 2, where W is a square diagonal positive matrix that associates a weight to each link in the graph. Infinitesimal rigidity is employed in continuum methods since it provides with a rigidity metric, the rigidity eigenvalue. Then, a framework is infinitesimally rigid if the rigidity eigenvalue is greater than 0. The rigidity eigenvalues also serve to quantify the degree of rigidity of a framework. Here we present our first contribution, an upper bound for the normalized rigidity eigenvalue, taken with edge weight equal to 1 and for two-dimensional frameworks. So, if we have a framework with m edges, graph diameter d, and an algebraic connectivity, then the algebraic connectivity is less or equal than the inverse of d squared. And since the rigidity eigenvalue is bounded by the algebraic connectivity, a result that is present in the literature, then equation 4 follows. This bound is powerful since it's independent of the agent's positions, and it also suggests that when d is large, the convergence rate of the consensus estimators degrades, because it strongly depends on the algebraic connectivity. Also, employing the rigidity eigenvalue as a metric might not be appropriate in such cases. So, here arises the idea of subframeworks. We arrange a framework in n subframeworks, each one associated with a single agent called the center of such subframework. The ith subframework is determined by the extent, which is the number of hops from the center in which other nodes are included. For example, in figure 2, we can see a subframework with center in the ith node and an extent of 2. Then our second contribution. A framework is infinitesimally rigid if and only if there exists a set of extents such that every subframework is infinitesimally rigid. This theorem translates framework rigidity, which is global in nature, to a set of n local conditions related to the subframeworks. However, having subframeworks with large extents augments the loads and latency of the communication channels when nodes need to broadcast information within their subframework. So we define the ith rigidity extent, which is the minimum extent that makes the ith subframework rigid, and the worst case rigidity extent, which is the maximum extent among all nodes. So we propose a decentralized controller to guide a formation using relative distance measurements only. The control objectives are 3. The first one is to maintain the framework rigidity, the second one to minimize the total communication load, and the last one to avoid collisions between agents. To contemplate a dynamic topology, we set the weights in the matrix W with a logistic curve that is close to 1 if two robots are within the range of conditions omega and close to 0 otherwise. So, the first control objective, the rigidity maintenance. The strategy adopted is to maintain the positivity of the rigidity eigenvalues of all subframeworks, which imply the rigidity of the entire framework. We define a subframework-based function that penalizes low values of the rigidity eigenvalues, as in equation 8, The ith robot follows the negative gradient of the functional phi, which has terms equal to 0, since the ith node is not included in every subframework. The non-zero terms, which have to be computed, correspond to the set of subframeworks that include the agent I. We call that the inclusion group of I, and we can see that in figure 3. The second control objective. To quantify the total communication burden, we propose as a framework-based metric that sums up the number of connections of all nodes in a subframework. This models the worst possible case when the ith node broadcasts a message and it gets retransmitted by every other node in the subframework. Weights are employed to account for the more intensive usage of the edges near the center. The ith robot follows the negative of the gradient of the functional L, which also has non-zero terms only for the inclusion group. And the last control objective. To avoid collisions, it is sufficient to consider only adjacent nodes, since in this world we can assume that non-adjacent ones are far away from each other. So the collision avoidance function consists of the inverse of the distance between neighboring agents only, and its gradient can be computed with nearest neighbors communication. For the localization scheme, we propose a distributed Kalman filter to update the estimated positions using range measurements from neighboring agents. Under reasonable conditions, this scheme ensures that the estimates convert to a formation that is equal to the true positions, up to rotations and translations of the entire framework. To eliminate this ambiguity, we select D robots and provide them with absolute position measurements, which is sufficient in the D-dimensional space. So, how to implement this in a decentralized fashion? Well, each robot implements a discrete version of the gradient descent of the functional shape that sums up the three objectives. Note that expression in 15 contains information only of the inclusion group, so no global data is required. Our last contribution says that the information exchange required to apply 15 in a decentralized fashion is completed in a finite number of iterations that is equal to twice the worst-case rigidity extent. To implement this, the ith agent must send its current position to its inclusion group through at most 8 hubs, as is seen in the left of figure 5. Then each red node computes a term in 15 and broadcasts it to I. This information exchange is completed faster than the consensus base if 2 times eta is less than the diameter of the graph, which is the minimum possible number of iterations required in such algorithms. So, to validate our approach, we present simulations for a formation of 60 agents randomly located within a region of 100 by 100 meters. The communication range is set to be 40 meters, and the rigidity extent of each subframework is set initially and then remains constant. So we can see here in the left pane the arrangement of robots and their connections. Solid markers correspond to the true robot positions, their colors indicate the extent of the associated subframework, and the red crosses are the estimated positions, which will rapidly get closer to the true ones. As the simulation runs, we can see how at the beginning more edges are constructed, augmenting significantly the rigidity eigenvalues and also the communication load. Then the controller manages to expand the network in order to reduce the number of links and the communication load without degrading the rigidity eigenvalues. And finally, we can see an emerging regular pattern, which is a consequence of maximizing the rigidity eigenvalues. So, let's take some conclusions. The subframework-based rigidity demonstrated to be helpful for the decentralization of the rigidity control. Unless extents are restricted to one hop, it tends to augment the communication burden. However, by including a communication load function in the control scheme, we could improve the situation. Finally, for future work, we plan to extend the scheme to include specific application goals, such as coverage, mapping, patrolling, and so forth, to study the impact of the delay associated with the multi-hop communications in the overall performance, and finally, to give the control scheme the ability to modify the subframework stance on the fly. That is all for today. Thank you, and I'm open to questions.